Yeah, and I want one of the take-home messages I want is that we can analyse the same data against the same null with two slightly different hypotheses. So, sometimes the Fisher test works, and sometimes it screws up for one reason or another. Chi-squared for larger numbers. Do both, and then you don't need to go berserk over this. Just say, well, they give about the same data. But if they come out with very different answers, and they do sometimes, that's a flag.
So that allows us to reject the null hypothesis that the distributions were identical.
Yes, that's right. That's correct. They're both testing the same hypothesis, but with slightly different technical assumptions. I don't want to go into it in too much depth. Frankly, the reason given for using the chi-squared is that it's easier numerically. And Fisher's quite a pig computationally. There's a lot of work in it. But R takes the strain now. So the conventional wisdom, when I learnt it, I was taught chi-squared is a nice, fast, easy thing to do, and Fisher's test is a mathematical dog's breakfast. But R takes the strain now. So I don't see any reason at all to use the chi-squared. Well, I sort of do. The thing that gives you chi-squared is that if you're doing education or Fisher, it doesn't matter. If you're doing your portfolios, it gives you an expected matrix. And then you can say, oh, look, this one's bigger. And oh, look, that one's smaller. Why is that? And oh, look, the boys have done very well at maths and the girls have done very well at, or whatever it is. So the advantage of the chi-squared is not mathematical. Chi-squared for larger numbers, that's what you use, that's what the conventional wisdom is. But it gives you an expected table which you can look at and talk about. And Fisher's exact test doesn't do that. Yeah, usually you are not supposed to use the if any of these numbers is less than, I think, 5, and one of them is, that normally disallows the chi-squared test. If you've got a 0 in there, you shouldn't use the chi-square test. If any of the expected values are less than 5, that's conventional wisdom, but frankly, I think it's a load of hog. I think it's a perfectly valid test, even if there's a 0 in there, you've got trouble because you're dividing by a 0. But if any e expected value that's the conventional wisdom anyway. And it's along the same lines as having an observation. It's along the same lines as having 30 observations to use the t-test rather than the z-score. Excuse me. Right, I'm going to spend the majority of today, and I've spent longer on that than I intended, talking about regression. We made a start on regression last time, and I'm just going to make a couple of non-mathematical observations about it. Sugar beet growth. Equals 1 year. And you can collect a nice data set like this, and it looks like that. So what you've got along the horizontal axis is number of camping holidays in a given year, and the vertical axis is sugar beet growth. And of course you can draw a straight line through it. Negatively correlated. I'll cover exactly what correlation means, but later. Negatively correlated. This is just what happens. This is an observable fact. what's happening here is a peculiar phenomenon called a spurious correlation. It's a spurious correlation. And it's caused by the fact that in any given year, if it's raining lots, then if it's raining a great deal, then the sugar beet grows very well, but there's nobody goes camping because it's raining. And here, and years like this, it's a beautiful sunny year. Everybody goes camping, but the sugar beet can't grow because there's not enough water. So it's a spurious correlation, or I think it's called hidden variable. Rainfall. So really what you should be doing is correlating these two separately against rainfall and saying if it's raining, nobody goes camping, and separately, if it's raining, then the sugar beet grows really well.
Is that what they call a confounding factor?
Yes. Is it a confounding factor? Yes. Confounding means something slightly different, but yeah. So that's what's going on here. However, if I were to forget about if I just forget this explanation here, if you didn't know about this rainfall business, let's just say that you were a bunch of farmers and you said, right, what we want to do is we want to increase our sugar beet growth. Let's stop these people from going on camping, because when people come camping, our sugar beet doesn't grow. I know, every time we see somebody camping, we'll send dogs or whatever and get them off. Get off my land. Because it's interfering with my sugar beet. Well, no, it isn't. They're both responding separately to the same hidden variable. The way to express this is correlation.
What's funny is some people actually think like that.
Oh, yes. It's a pernicious problem. It's a pernicious, difficult, horrible problem. Does not imply causation. Correlation does not imply causation. Just because two things are correlated doesn't mean that you can control one with the other. And yes, some people do think like this, and it's nonsense. You can dismantle it straight away, but it's very, very, very difficult to tell what's going on. You get it in health sciences all the time. So you get educational attainment against the whole thing. Before you know where you are, you're in a minefield.
Climate change.
Well, yes. Yes, I've got quite a lot to say about that.
The other example we've been given for that was ice cream sales and drownings.
Ice cream sales and drownings. Oh, nice one.
Ice cream sales go up, so do drownings. But,
Oh, well, let's do that one. Ice cream sales
yeah.
against drowning. And of course, it's a hotter day, so everybody goes swimming and ice creams. So, okay, so the National Drowning Panel comes along and says, right, well, we'll just ban ice cream because ice cream sales cause drowning. The best example I know is if you get health and safety things, you might find, nationally we've got a big problem with headaches. People have got a lot of headaches in the morning and they can't work effectively and they're causing accidents and you can't learn effectively if you've got a headache. So we'll do a big study of this because it's important. And we've discovered there's a huge correlation between having headaches in the morning and going to sleep with your shoes on. Well, of course there is. And so you get this national campaign saying, remember to take your shoes off before you go to bed. Take your shoes off before you go to bed. Don't go to bed with your shoes on.
You might as well cut down on the drinking so you don't forget to take your shoes off.
Correlation does not imply causation, and it is a pernicious problem in statistical analysis. Of course, as you say, cut down on the drink, and then you won't have the problems. You won't fall asleep with your shoes on. But if I say something like high blood pressure causes strokes, and I give you drugs to control your high blood pressure on the basis that high blood pressure is correlated with strokes, wait a minute, Maybe the high blood pressure is the body's response to something else going wrong in your environment. So I cut down the blood pressure. That's just the same as telling you to take your shoes off. And you're in a very weak position if somebody says to you, correlation does not imply causation. Before I forget, the equation we used was yi where A and B are your coefficients. The equation itself, and you'll remember we were trying to estimate A and B in terms of maximum likelihood. You'll remember that the epsilons, the errors here, were identically Gaussianly distributed. Epsilon I was Gaussian, IID Gaussian. So causality is built in to this equation. So when you're trying to estimate A and B, there's causality built into that because look, X does some stuff and gives you Y. There's no question of going to bed with your shoes on gives you a headache. There's no question of eating ice cream makes you drown. There's no question of, what was the other example? Sugar beet makes you go camping, or whichever way around it was. And there's another feature of this as well. We've got drowning versus ice cream. I don't want to go into the mathematics of this because it tends to get a bit complicated. But I could equally well draw drowning and ice cream here. And we get a different picture for sure. But all I'm going to do is take that and flip it round. It's a different line. It looks like it's going to be the same, but it isn't. The lines are different. Well, you can tell the errors are different because these errors go vertical. The errors always go vertical, but that corresponds to an error here is an error in drowning, and an error here is an error in ice cream. So you see, when I flip my x and y axes across, purely because there's a doubt or uncertainty as to what's causing what. Is the ice cream causing the drowning, or does the drowning causing the ice cream? Well, neither, of course. But if you're in any doubt about it, you've got two different regressions, and the mathematics is different because the errors are in the y-axis in both cases, and the y-axis changes. Okay, so regressing x against y is different from y against x. It's a minefield. I'm going to go back to trees. I say I was a little bit out of sync with myself yesterday because I wanted to head trees. Here we go. So I started this, and you'll remember that we've got a whole bunch of trees and we want to predict the volume. Just thinking about causality, I think it's reasonable to say that a high girth tree has got a large amount of volume. The girth does cause the volume, doesn't it? I think it's reasonable to say that the height does cause the volume to increase. I don't think the volume affects the height. I think these two things cause the volume. That's a reasonable thing to say. And also, it's reasonable to put volume on the y-axis rather than the x-axis because I'm trying to predict this because I sell the wood. So I think we're on firm ground here when we talk about correlation not causing, correlation not causing, correlation implying cause, you know what I'm trying to say. Implying causation.
Try it again.
We're on firm ground with correlation implying causation here, because we're starting with causation. Let's go back to plot volume is a function of girth data equals trees. And I'll just tart this up a little bit. If I give it PCH equals 16, that's point character equals 16. It'll just make the points a bit more visible. There you go. Oh, it doesn't like point character for the linear model. Let's just think about what this means. I've got the volume equals A plus B times the girth minus 36.9 plus 5.066 times the girth plus error. Now, on the one hand, this is quite a good model. In the sense that the line goes through the points. On the other hand, it's a poor model because line goes through the points. But on the other hand, it's a bad model because girth equals 0 implies that the volume equals minus 36.9. So it's a good model because it goes through the points. There they are.
What's the E?
Volume equals A plus B times the G for girth. And I'm just making the observation that if I set G equals 0 for a zero girth tree, you've got a negative volume, because that's what the intercept is. Are you happy with that? Yeah? And you can kind of see what's going on. Here's my girth. If I produce this line down here, here's the girth 14, 12, 10, 8, 6, 5, 4. It's down here. In fact, I'll draw it for you. Let's go back to my plot. That's my plot. If I say x lim equals 0, all I'm going to do is make it plot it with the x-axis being limited between 0 and 25 instead of the default. Now you've got a very different picture. There's your zero girth tree. You can see that this line will intersect the x-axis, the y-axis at a very small value. I can change the y-axis as well, which I'll do now. Oh, it should be even smaller. What was it, minus 36? You see, it's gone down to minus 40. So now if I put my line on, yes, it's a good fit inside the data, but as soon as we extrapolate, we get into nonsense land because we get into negative volume land. So that's a poor model for that reason. Now, there's many ways around this. And really, the take-home message from everything I'm going to say today is there's no one right answer. What I'm going to do is give you lots of different types of regression, and each one will have strengths and weaknesses, and there's no overall best answer. So it's bad because it's got this negative region here. But nevertheless, inside the region, it's quite a good model. So which way around it does this go? I'm not altogether sure. That's not. It's not sure whether it's not clear to me whether this actually matters. Sometimes it does, and sometimes it doesn't. Let's go back to my plot. Actually, if I add 0 plus girth, what that does is this. It's plotted a new line on the graph here, which is constrained to go through the origin. So that 0 plus, oh, it's behind here, just a minute. I'll just make it a different colour. There we go. So now we've rescued it from predicting negative volumes, because at 0 girth, we've got a 0 volume now. Because I put this 0 plus terminology, it means don't have a constant, basically. You happy with that? But you can see that it's taken this line that we originally had, which is our standard regression line, it's gone and pulled it here to go through this point here, which is constrained by the FID. And it doesn't fit the data as well. So you've gained something which is non-negative volume, but you've lost a good fit as well. So that's a trade-off. In this case, I would be inclined to go with the original thin line and say, well, suck it if it's a small girth.
Negative girth, negative volume, you got no tree,
Well, you haven't got a negative. Well, if you've got a negative, well, see, this red one isn't perfect either, because if you've got a negative girth, it kind of doesn't work. Okay, let's go back to the data. I'm going to stop in a minute. Actually, I'm going to stop right now. What I want you to think of in the break, I'll take a break for 10 minutes. I want you to think of how you can use regression and how you might have different forms of regression for the data you're considering in your portfolios. Okay? I want you to make sense of regression in your context about your data. I'm going to stop for 10 minutes and I'll reconvene at 10 past 10.